Direct comparison test. Let 0 be less than a sub n, less than or equal to b sub n for all n. If an infinite series from 1 to infinity of b sub n converges, then the infinite series from 1 to infinity of a sub n also converges. The second part of this is if the series of a sub n diverges, and then the infinite series of b sub n diverges. It may be a little hard to interpret those two statements. Informally, the test says if the larger series converges, then the smaller series must converge. If the smaller series diverges, then the larger series must diverge. Let's take a look at what that means. Got some examples under here. Determine the convergence or divergence of each infinite series. In our first example, we have the sum from 1 to infinity of 1 over 2 plus 3 to the n. Now, since 1 over 2 plus 3 to the n can be made smaller than, and let's think about this. Over here to the right in pink, we have the nth term 1 over 2 plus 3 to the n. That's very close to 1 over 3 to the n, which is a convergent geometric series. We want to compare this to something that we know for sure diverges or converges easily. Geometric and p-series are fantastic for these comparison tests. So that's actually what we're going to do is we're given a sub n, we're going to build b sub n, and we're going to write it as what we know as a convergent geometric series. Ratio is less than 1. If you want to make a fraction larger, one technique is to make the denominator smaller. So if I take off the plus 2, where it's 1 over 3 to the n, I have created a larger fraction that converges. Therefore, the smaller must converge. So this is a larger term in a convergent series. Therefore, the smaller term is going to make a convergent series as well. In the second example, we have the sum from 1 to infinity of 1 over 2 plus square root of n. Over here, excuse me, this is going to be comparable to 1 over square root of n, or you can also look at, because I have a feeling it's going to diverge, so I need to build something smaller that diverges as well. Now, if I try to use 1 over square root of n, it's actually not smaller because it has a larger denominator. But if we compare 1 over n, it has a larger denominator than this one, therefore it's going to be smaller term by term. 1 over n is a divergent harmonic series because it's a p-series with p equal to 1. That's divergent. Because our original nth term is larger than the one we built, an is bigger than bn. This one diverges. The larger one must also diverge. Limit comparison test is slightly different. We're going to take two positive terms, an a sub n, a b sub n. We're going to stack them in a fraction and take the limit as n goes to infinity. Now, if this limit has a value L that's positive and finite, then these two series must both converge or diverge. Limit comparison test works well for comparing messy algebraic series with a p-series. Let's investigate. First example, determine the convergence or divergence of this infinite series. Now, if you look at your dominant terms from top and bottom, that's 1 over n squared. Those are the dominant terms from each side of the fraction. So that's what we're going to compare with, is 1 over n squared. When you build your limit, you take your original term divided by what you build over here is your B sub n. Just remember B and build. Dividing by a fraction is the same as multiplying by its reciprocal. So technically it's this fraction divided by that fraction, but I'm going to take my A sub n and multiply it by my B sub n flipped over. Multiplying, we get the limit as n goes to infinity of this fraction. We have matching powers of dominance, so the lead coefficients of those terms will be your limit. That is positive and finite. Since we know that this is a convergent p-series, p equals 2 and that's greater than 1, that the original must converge also. The second example, the sum from 1 to infinity of 1 over square root of 3n minus 2. The dominant terms we have on top is just a 1, on bottom square root of 3n, or just simply square root of n. That's the most dominant. That's the one we build. So this is A sub n, B sub n. This is a divergent p-series because p is a half, and that's less than 1. Let's calculate the limit of A sub n times B sub n flipped over. That gives us the square root of n over square root of 3n minus 2. By property of matching radicals, that's square root of n over 3n minus 2. Our dominant terms match in power, so the coefficient's 1/3, square root of 1/3, that is positive and finite. Now we go back up, the one we built diverged, so the original must diverge also. That's how that works. Take the term you're given, build one very similar, calculate the limit of given over build, which is given times build flipped over. Find that limit. If it's positive and finite, then the one you built that's easy to determine will also tell you the result of the original. The sum from 1 to infinity of n squared minus 10 over 4n to the 5th plus n cubed. When we get ready to build, I always stress look at your dominant terms. N squared on top, n to the 5th on bottom, and that's how we build it. N squared on top, n to the 5th on bottom. That does reduce to 1 over n cubed. Since p is 3, greater than 1, we know we have built a series that converges. If our limit comes out positive and finite, then the original must also converge. So let's check it out. The limit, we've got the original A sub n term, divided by the B sub n would be like multiplying with it flipped over. Distributing, that's n to the 5th minus 10n cubed over 4n to the 5th plus n cubed. Our dominant terms in this limit, we have both n to the 5th, so we take their lead coefficients, that's 1/4, and it turns out that that's positive and finite, so whatever we have for our build, in this case convergent, our original infinite series must also converge.